Hi, my name is Melissa Pesce-Rollins, and I'm going to talk to you about Fermi-Large Area Telescope's observations of the flaring sun. So let me turn on my slides here. I hope you can see this okay. And so I wanted to start with a brief introduction on the actual emission from gamma ray solar flares. So the main source of energy release and consequently particle acceleration is believed to be magnetic reconnection. And you can see that in this cartoon here on the left. So when this phenomena occurs, these particles get accelerated, then they travel along field lines. There's some open field lines, and then they go out into space, and there's closed field lines that allow the particles to precipitate back down to the denser part of the solar surface. Products of these accelerated particles, emission products, are typically Bremsstrahlung, as well as de-excitation lines, neutron capture, as well as a nice continuum above 30 MeV. There's a nice example shown here on the right of a flare observed back in 1991 by the observatory CGRO. And this shows you exactly all of the signatures that I just mentioned. So what you can gather from this spectrum is that from just observing one flare, we can gather a wealth of information on the particles that have been accelerated, to which energies they've been accelerated, as well as information on the ambient medium of the sun itself. There are signatures of particle acceleration also far from the flare site, and for example, many bright flares are associated with coronal mass ejections, which are significant release of plasma and accompanying magnetic field from the solar corona. Now, these phenomena create shock waves that move quickly away from the sun and out into space. For decades now, we've have observations of solar energetic particles observed from Earth, and a subset of these particles have been shown to be accelerated by these coronal mass ejections. And there's even evidence for ion acceleration up to GeV energies. Other signatures of particle acceleration far from the flare site can also be seen in radio and microwave frequencies, and these are called radio bursts. Now, these are caused by non-thermal electrons, which are accelerated again at coronal or interplanetary shocks, and they're often associated with CMEs as well. Here I'm showing a nice image of a CME here on the left. I'm showing a nice image of a CME seen from the coronagraph of SOHO. And on the right, I'm showing also a power spectrum illustrating two types of radio bursts that can occur during flares. So I'm from the Fermi-LAT collaboration, so obviously I really like to talk about Fermi. And here is a cartoon of the satellite up in space. There are two instruments on the satellite. There's the gamma ray burst monitor, which observes the entire unocculted sky in the energy range between 8 keV and 40 MeV, and it's dedicated to studying short transients, such as gamma ray bursts, but also solar flares. There's also the Large Area Telescope on board, and this is it has a large field of view. It observes about 20% of the sky at any time, and in the energy range between about 20 MeV to above 300 MeV. And it observes the sun between 20 to 40 minutes every 3 hours. So with the increase in sensitivity of the LAT with respect to previous space-based gamma ray missions, we've been able to significantly increase the number of gamma ray flares observed. And I hope you can get an idea of how much we were able to do that by this plot that I'm showing here. Now, this plot shows the number of solar flares with emission greater than 25 MeV over the past 40 years. And you can see how much Fermi has been able to contribute in increasing the sample of solar flares here. So with the end of the last solar cycle, the 24th solar cycle, we published our first Fermi-LAT solar flare catalog. And in this catalog, we found that more than half of the sample in our catalog is associated with relatively modest X-ray flares. Now, this was surprising because prior to Fermi, all of the gamma ray solar flares were all associated with the brightest X-ray flares. What we also saw was that half of our flares, half of our sample, have an extended emission lasting more than 2 hours. So again, this was also a surprise because prior to Fermi, there were long duration gamma ray flares observed, but there were very few. And so it was thought that it was a fairly rare event. Instead, with this sample, we find that acceleration of ions above 300 MeV is actually fairly common. So with this sample, we confirmed what was already previously suggested, that there are two phases in gamma ray flares. There's the impulsive phase, which is pretty much coincident with what's happening in X-rays, and there's also the delayed phase. What's interesting, though, is with this increase in sample, we are able to, the data really is suggesting that there is an additional acceleration emission that is driving the delayed phase that still needs to be understood, the origin of this additional mechanism. So I mentioned that there were different phases in flares, and I wanted to give you an example of a beautiful flare that we saw back in 2017 that illustrates multiple phases. So here I'm showing on the right-hand side is the time profile of the first roughly 40 minutes of the flare. And the top panel shows you the X-ray activity. The middle panel shows you, the middle panel shows the Fermi-LAT flux, and the bottom panel shows the proton index of the ions responsible for the gamma ray emission. Now, what you can see here is that the first part of the flare, the emission all seems to coincide with the X-ray activity, and you also see that the proton index has a tendency to soften with time. What's interesting, though, is that once the X-ray flare dies off, the gamma ray emission, the flux remains essentially constant with time, as does the proton index. Now, I want to emphasize here, though, that the flux in gamma rays, it may be constant, but this is still roughly 1,000 times brighter than the quiet sun level. So this is incredibly significant. It's just constant in time. Now, if you go and look at the left-hand panel, this is a zoom out of the entire duration of the flare. This flare lasted for about 10 hours. What's striking here is that we saw essentially two phases happening during the first 40 minutes, but when you go and look at over the entire range, we see that when the sun comes back into the field of view, that's why you're seeing these little gaps between the data points. That's because the sun is not always in the field of view. So when you look and see when the sun comes back into the field of view, the emission is still very bright. That middle panel, you see that the emission is still very bright. However, you do see that the proton index has gone back to the hardest value that was seen during the prompt emission. So again, another phase is happening here, and then it proceeds to soften with time. So this is a perfect example of we're seeing different phases happening during the acceleration. Another innovative aspect of the LAT is that we're also able to finally localize the gamma ray emission from these solar flares. So for the brightest flares, where we have sufficient statistics, we found that the prompt emission coincides fairly well with the active region from which the other flaring activity was occurring. And that's what you see here on the left panel. You're seeing that red circle there is giving you the localization of the greater than 100 MeV emission from Fermi-LAT. And that little bright spot is the flaring active region. Now, for flares that have long duration emission, we're able to see that the localization as a function of time actually drifts over the solar disk. So this is actually a pretty special case, and it is suggestive of a spatially extended component, that something is really drifting along as time goes on. So as I mentioned in the first slides, that particle acceleration seems to be occurring at the coronal mass ejections. What I didn't mention yet is that essentially all of the flares in our catalog are associated, all except for 3, are associated with fairly fast coronal mass ejections. So it's fairly natural to go and search to see if there's any correlation with what's happening with CMEs and what's happening in gamma rays. So what you see here is a very simple scatter plot of the CME linear speed versus the peak soft X-ray flux for all of the flares during the last solar cycle. In blue, you see the flares detected by Fermi-LAT, so that's the sample in our catalog. Filled squares are flares that occurred that were not seen by the LAT, but were in the field of view during the flare, where empty circles are just flares that were not seen and were not in the field of view at the time of the flare. So from this scatter plot, you can get some general idea of the favorable conditions for gamma ray emission to occur. And what you see is, of course, that when we have very fast CMEs and very bright X-ray flares, we are able to detect 86% of the flares occurring. So that's clearly the most favorable condition. But what's also interesting is that these quadrants and diagonals, so the first quadrant 1 and quadrant 4 are essentially equally favorable. So the CME speed and the GOES X-ray flux seem to kind of compensate each other. So when there's a weak X-ray flux, X-ray flare, but a fast CME, we're equally probable to detect gamma ray emission as if we have a slow CME and a very bright X-ray flare. So this is also valuable information to keep in mind. So as I said, solar cycle 24 is finished, and we're entering in solar cycle 25, and we're already starting to detect new flares. So we have lots of exciting science coming up. What's really exciting about this new solar cycle is that there are several new solar dedicated observatories online and taking data. I put together this little snippet of pictures, and of course this is not exhaustive. There's many other detectors that I wasn't able to put in here, so if I forgot your favorite instrument, please forgive me. It's just illustrative purposes. But what I want to say, that the most important thing is that by collaborating together, sharing our data, and analyzing over multi-wavelengths, we will be able to finally gather the details needed to distinguish between the acceleration scenarios that have been put forth within the community. So at the risk of sounding a little cheesy, I must say that the future really is bright. Thanks.